Hello everyone, my name is Xavier Rene-Corail, and I will present to you Security as Code, an approach to help the adoption of DevSecOps. First, a few words about me. During 10 years, I was in charge of deploying software practices and culture in a fintech company, extreme programming, TDD, DevOps, Agile. And now, as head of the GitHub Security Lab, I'm trying basically to do the same with secure code for open source developers. A few words about what I'm doing now. I'm leading the GitHub Security Lab. In the GitHub Security Lab, our mission is to help secure open source. So we audit code, we report security vulnerabilities to the maintainers, and we use this research work to publish educational articles, trainings, workshops, or to write automated checks. We also provide high-quality security advisories to notify the entire ecosystem of potential security vulnerabilities that they may find in their open source dependencies. We do all of this for free for open source, and more importantly, we try to build a community of people willing to contribute to this effort for open source projects. Today, my session is to present the approach Security as Code to help the adoption of DevSecOps. But let me start with a short science fiction story. You have all seen, I guess, the landing of the Perseverance Mars rover a few weeks ago, and our CEO, Nat, tweeted that our CodeQL product was used in the drone flight software. Actually, CodeQL was already used by NASA engineers 9 years ago. So, 9 years ago, the Curiosity rover was about to land on Mars, and the NASA engineers discovered a critical bug in the control software that would likely prevent the opening of the parachute during the landing. The pseudocode that you see here explains the bug. In C, even if the parameter of a function is declared as an array of size 12, you can pass, nothing prevents you to pass an array of any size as argument of the call. So you can pass an array that is shorter, and in this case, the result is unpredictable. The bug was patched mid-flight and deployed remotely on Curiosity. But the NASA engineers were afraid that there would be other variants of the same bug. So they used CodeQL to check the code. The query that you see here searches for cases where the argument is an array of a size that is shorter than the array size of the parameter of the function. By running these few lines, they discovered no less than 30 variants of the same bug. Some of them were critical and could have caused the rover to literally crash on Mars. And here I'm talking about a physical crash, not a software crash. So they fixed them mid-flight, and they deployed them, and so that the rover could land safely on Mars. How cool is that, right? But you know what would be cooler? What would be cooler is if all open source developers could use the same approach to secure their code. And this is what I'm talking about today. So let's first begin with the specific challenges that we encounter when we want to shift security left. So first, why shift left? Because it's cheaper, it's more effective, it's more efficient. Look at the NASA Curiosity examples. You can imagine the cost difference between finding the software crash during the testing phase and finding the actual rover crash when landing on Mars, right? I will first address some misconceptions about shifting left. The first misconception is that it stops at the coding level. No, there are activities, software activities at the left of the coding phase, requirements, architecture, design. So you have to shift left up to these activities. But it's out of scope of today's talk because I only have 30 minutes. So basically I will stop at the coding phase. I will do exactly what I just told you not to do. I will stop at the coding phase. The second misconception is that it's not just about automating and running earlier. I saw that many times, asking testers, ops, security teams to just automate what they're doing and run their tools earlier in the process. At the beginning, it gives you a false impression of success because, of course, you're automating stuff, you're running more often, cool. But after a while, it stalls and it fails because it doesn't deeply change the developers' practices. So what do we need to change the developers' practices? What motivates developers? In his book, Drive, Daniel Pink tells us that it's a combination of autonomy, mastery, and purpose. Autonomy is about being free to do stuff, being in control. Mastery is about being good at what you're doing. Right? Like, for example, people like to learn music instruments because they just want to be good at it. And purpose is about knowing why you do something. So now, if you take my example of another team just running the automated tool and running it earlier in the process, and then just generating a deluge of Jira issues for you to fix, then clearly you're not autonomous. You are not in control as a developer when that kind of things happen, right? In that same example, the expertise stays in that team, and you don't learn anything in the process, right? So you don't improve, you're not good at what you're doing. And lastly, purpose. Well, in that case, you are just fixing a bug because the experts said so in the issue that is generated, but you don't really know why you are fixing that bug. So clearly, this is a big misconception. You don't just have to automate and run earlier. You really have to give the developers autonomy, mastery, and purpose if you want these practices to stick. So now let's see what is specific with security when it comes to apply DevSecOps practices. So first, what is common with the DevOps problem? Well, the divide, basically, the divide between the communities, the divide that we had between developers and testers, and that we saw between developers and ops, and we find the same divide between developers and security teams, right? Like, testers were told that they must not trust the developers. And then we had ops that were measured on stability of the system, while developers were measured on adding new features to the system. It's the same for security. Developers are asked to develop features faster, to make things easier for the end user, to optimize the product, and this can happen to be incompatible with security requirements. So we have the same divide here. But what is specific? First, the criticality or the urgency of the security bugs. Some security bugs can jeopardize the entire integrity of your system. They can leak personal data from you or from your customers. The second specificity is that security researchers are quite a rare population compared to developers. And so mechanically, they are not always available to help. They are less available to help. And the last thing, and this is especially for open source, there is a perception that security researchers have bad intentions, like they are not here to help the open source projects, but they're rather here for getting money for the bounties or for their personal reputation or for just the fun of attacking software. So at the end of the day, there is this divide, but the divide is, I would say, at another level, really. So what did we learn from DevOps that we can apply to DevSecOps? So first of all, we should align the goals. Like what we did for testing and for ops, well, we decided that the goal of QA was not to find bugs, but it was to prevent them, right? And then we say that the goal of the ops is not stability of the system, but it's decreased downtime. Basically, we found goals that could be common for dev and testers, for dev and ops. So in an organization, you should do the same and find a goal that could be the same goal for your development team and your security team. In open source, here an example of what we do at the security lab. we have a bounty program. Okay, but instead of paying hunters to find bugs, to find security bugs, we pay hunters to write automated checks that prevent those bugs. And these checks are free for open source. We have seen the purpose, align the goals. Now, how do we give developers autonomy and mastery? Well, in the DevOps movement, we give them developer tools, right? That they could autonomously run, that they could learn, that they could master. We also put testers and ops on the same team, and we said, hey, testers, ops, you will be acting as experts who support developers, but ultimately the developers will be accountable for the bugs, right? The person who commits the code is accountable for the bug. In particular, I observed that one of the successful levers for DevOps adoption has been infrastructure as code. The developers were excited just because it was code. They could read it, they could understand it, they could contribute to it. Ops were finally speaking their language, and they were transmitting their expertise to developers through code. And the same is true with the adoption of testing by developers with unit test frameworks or functional test frameworks like Fitness, Cucumber, or Selenium. So could we do that with security? So yes, with security as code. And now I will show you how we are doing that with CodeQL. As I showed you with the NASA examples, CodeQL helps you find vulnerable patterns in your code. How does it work? CodeQL extracts your code into a special database. It will extract the abstract syntax tree, the semantics information, the control flow graph. And then once it's done, you can query this DB as you would query any other DB. But you will not do that with a simple SQL query. You will do that with an optimized object-oriented language based on Datalog. Okay, let me show you a quick demo of what that looks like. So, I am in my VS Code editor, and I cloned the VS Code CodeQL starter GitHub repo, which gets me started with some queries in several languages. And I imported the CodeQL DB of an open source project which contains a security bug. Let's first have a look at the bug. So I'm here in the Min.io project, which is an Amazon S3 compatible object store. The bug that I'm about to show you has been fixed since, of course. This function validates at main signature, as the name says, validates that the request comes from an admin. Here, we are checking that the request is authenticated. And here, if there is an error, then we log the error, which is good, but we do not return. We do not return the error. Instead, we continue treating the request. So this is a critical bug that allowed non-admin to get access to admin privileges. This bug has, of course, been fixed by adding a return statement here, line 143. So let's see if we can find this pattern with CodeQL. What we are looking for is the check of an error code in which there is no return statement in the then branch. So let's begin with that. Let's have a look at the example that I prepared to you. The query starts by importing the Go library. As I told you, CodeQL is a language, so you benefit from a lot of reusable libraries from the start. And then all the queries are under the form from where select, really as if you were querying a database. In this example, we are looking for all the if statements. This is the type definition of the of an if statement. We are looking for all of if statements whose then branch does not contain a statement of type return statement. So let's run that query to see what we get exactly. So here, when I run the query in my VS Code editor, I get the results from my code. So if I look at one of these results, for example, then yeah, I can find that it's an if statement and that there is no return statement in the then branch. Let's have a look at another one. Okay, here, same thing. It's an if statement and there is no return statement inside the then branch. Okay. Now, in our query, we don't want all the if statements, we want the error checks, right? So we want the if statements that are checking if our error if our error code is really an error. So let's have a look at the code. So yeah, basically we are interested in cases where I'm checking my error code against error none. In order to model that query, we need to know which types we need to query. So what we can do is use the CodeQL AST viewer for that. So if I have a look at my function, then I can find my function here on line 124. It's a function declaration. Inside that function declaration, there is a block statement that corresponds to the body of my function. If I jump to that line, then I find an if statement. Yep. And in this if statement, there is a not equal expression. And in this not equal expression, there are two identifiers, one being a variable name, one being a constant name. So here, thanks to this AST viewer, I've got all the types of the object types that I need to model my query. So let's do that. So we are looking for an if statement, a not equal expression, and an identifier. And then I need to join those three tables. I will say that my if statement has a condition that is the not equal expression, and that one of the operands of this not equal expression is my identifier. And then I will filter on this identifier saying that the name of this identifier should be none. Okay, if I launch that query, okay, by running this query, I can see that I get 5 results. Let's have a look at the first result here. Okay, this is a if statement where I check against none and the then branch does not return. So that's good. Here it's my bug. So that's good. My query finds my bug. Okay. Let's have a look at that query. If you look at it, it really looks like a SQL, right? You declare the tables, you define your joins, you define your filters, and then you select the results. But as I said, CodeQL is a language that allows you to define your query in a much more elegant way. Look what I can do. I will get rid of all of this, and I will just say that my if statement has a condition that is a not equal expression. So I can cast it into a not equal expression, and this not equal expression has an operand that I can cast into an identifier whose name is none. And when I run that query, I get exactly the same results as before, including my bug. So you see, with this language, instead of just running a SQL, you get a way to express your vulnerable pattern in a much more readable and much more elegant way. Now, imagine that you don't have a case where you are checking that your error code is not equal to none, But you have a case where you are checking that your error code is equal to error none. And in that case, the branch in which you are handling the error is not the then branch, but it's the Lsponge. So how do you cope with that? So this is also where the language brings value. I will create a class that I will call error check to extend my if statement. I will define here the characteristic predicate of error check. I will just copy it from here. I will say that my object is an if statement whose condition I can cast into a not equal expression, whose operand is an identifier called error none. But I will not say that it's a not equal expression. I would say that it's an equality text expression to cover both cases of checking my error code against error none or with an equal or not equal. And then I will create a function get error handling branch. And this function, I will say, okay, if my condition is of type not equal expression, then the result of this function is my then branch. Otherwise, the result of that function is my else branch. And what I will do is that I will use that new class in my query by saying I want all the error check where my error handling branch does not contain a return statement. Let's run that query. Okay, so when I run that query, first thing, I get more results, of course, because now I am also handling these cases where I'm checking if my error code is error none, and here, well, there is not even an else branch, so the else branch doesn't return, and I still have my bug. Okay, let's have a closer look at the query. You can see that here, with that language, I can really read it as if it was just plain English, right? I'm looking for an error check where the error handling branch does not contain a return statement. Okay, so, but I also find a lot of false positives, right? I find my bugs, but I also find a lot of false positives because I'm interested in the case where the error is really important and should stop the processing of the function, right? But we should really limit our query to this bug's case and not get all the false positives. So basically what I'm looking for is a case where the error code that I'm checking is coming from the result of this function is authenticated. So basically we are already expressing that one operand of the equality test is error none, the other operand of the equality test should be a return to this function. But wait, the call to that function can be in another function or in another file event, so how can we do that? So I will show you the final query, because my goal here is not to show you, to run a product show, but how to implement security as code. So this is the final query, and that final query makes use of the CodeQL data flow feature. So this data flow feature allows you to track data flowing in your codebase across functions, across files, from a given point to another. You just have to create a data flow configuration, and then you declare in the code what is the origin point, the source, and what is the destination point of the flow, the sink. In our case, The source is the result of a call to isRequestAuthenticated. And the sink is the operand of an equality test. Okay? Once you have defined your source and your sink, you can call this function hasFlow. hasFlow will return true for any couple of source sink when there is a flow from the source to the sink. Okay, so what you will do is that we will evaluate this function to show you the results. Okay, let's have a look at this one. So this one, you can see that this is indeed a sink because it's an operand to an equality test. Okay. And it comes from a call to that function, but that function, it's in another file, and it calls that function, and that function calls our function isRequestAuthenticated. So, as you can see, we are able to track the data flowing from the call to isRequestAuthenticated to our operand to the equality test across different files. Okay, let's now use this data flow configuration in our class. So I create this predicate, am I checking an authentication result? By saying that an operand of my test equality is actually a sink of my data flow configuration. And then my query becomes, get me all the error checks where I'm checking an authentication result and where the error handling branch does not contain any return statement. Let's run that query. And that query gets me only one result, and that result is my bug. Okay, so we're back to our slides. So does this approach check all our boxes? So automation, yes, you get an executable query. There is a CLI. This query can run in your CI/CD. It's a developer tool, yes. This is not a report from a security team or for managers, right? It's for developers. It lives in your IDE, it lives in your pull request, as you can see in the screenshot on the left. If you're using GitHub, it's fully integrated with your pull request. And it brings you to your code for immediate action. Sharing knowledge? Yes, the security researcher can express their knowledge as code in the query, and the developer can read it, learn about it, learn by example by running the query on their own code, and they can contribute to it, they can act on false positives. It's basically a way to communicate with security researchers. And there is a bonus. The queries are open source, so this means that you benefit from the collective intelligence of the community. You benefit from a growing number of reusable libraries. You benefit from continuous improvement of the false positive ratio of these queries by the community. There are other tools that allow you to leverage the same principles. So I'm thinking about SemGrep or Coccinelle, for example, where you have this same community-powered security as code. If you compare them to CodeQL, they are less powerful. You don't have the data flow and tank tracking features that are so important for security, but on the other hand, they are simpler and the learning curve is shorter. Thank you very much for listening to me. So I wanted to show you one approach that would help the adoption of DevSecOps. And if you want to know more about security as code approach, please reach out to us. Also, of course, this is one approach, but I would love to hear out other ideas to promote DevSecOps. So please reach out to me or reach out to the GitHub Security Lab if you want to share them, if you want to contribute to our effort. Thank you.